In this video, we are going to discuss integration by parts. Integration by parts is a technique that can be applied to a wide variety of functions. It is particularly helpful when you have an integral involving the product of two functions. We know there's no product rule for integrals. Up to this point, we have not discussed how to integrate the product of two different transcendental functions. The method that we learned in this section will finally allow us to do so, or even two different algebraic functions. So we will be able to do that with the integration by parts method. With this method, we have ability to integrate functions such as x natural log of x dx, x squared e to the power x dx, e to the power x sine x dx. As you can see, none of these can be worked out with U substitution. U substitution is not going to help in any of these problems. So integration by parts is another tool we have in our toolbox when we are trying to evaluate an integral. It all actually comes from the product rule. If you recall, what is the derivative of function u times function v? It's u dv plus v du. So u derivative of the function v with respect to x plus v derivative of the function u with respect to x, where both u and v are functions of x. It can be also written as uv prime plus vu prime, where both u and v are differentiable functions of x. If u prime and v prime are continuous, we can integrate both sides to obtain this equation. So if I go ahead and integrate, let's see what do I come up with. So I'm going to, on the left-hand side, derivative and antiderivative, derivative and integral are opposite of each other. I'll be just left with uv. And then uv prime dx would turn into u dv integral plus v du integral of v du. From here, we are going to manipulate a little bit. We're going to move the v du to the left-hand side. If we do so, we are left with u dv, integral of u dv equals uv minus integral of v du, where u and v are continuous functions of x and have continuous derivatives. So remember, this is the formula for integration by parts. Memorize this formula. Okay. Guidelines for integrating by parts. Try letting dv be the most complicated part of the integrand that fits a basic integration rule. So dv, you want dv to be something that is easier to integrate, and u will be the function that you will find the derivative of, okay, whose derivative is simpler than the u itself. Again, something that might help us choose the u and dv is liet. Let u be the first thing on the list. So liet, L stands for logarithmic functions, I stands for inverse trig functions, A stands for algebraic functions, T stands for trig functions, E for exponential functions. So whatever comes first on this list, let u be that function. Okay. This rule does not help when both the functions fall in the same category. For example, if you're dealing with two algebraic functions, you will not be able to use this rule. Okay. If you're dealing with two trig functions, you will be not able to use this rule. If you're dealing with two exponential functions, you won't be able to use this rule. Okay, most of the times this liet rule does help you out. Remember that. And also remember the integral of u dv equals uv minus integral of v du. Okay. Again, it comes from the product rule. We just showed you really quick how to derive this. So I'm doing a lot of examples of integration by parts. Okay, the first one is integrate x times cos x dx. So how can I integrate cos x times x dx? To integrate x times cos x dx, I need to decide what function is my u and what function is my dv. Okay, think about Liat. Do you have a logarithmic function? No. Inverse trig function? No. Algebraic function? Yes, you have an algebraic function which is x because you have a product of two functions. So let u be x and the remaining portion of your integrand be dv. Okay, now go ahead and do the derivative of u. Du will be equal to dx, and go ahead and integrate dv. So we're going to get v equal to integral of cos x. Integral of cos x is sine x. So now remember that formula for integration by parts is u dv equals uv minus v du. Now we're just going to plug all the values in. U is here, v is here. So u dv, or I'm sorry, u times v is equal to, let me start with the left hand side. U dv. U is x, dv is cos x dx. That integral can be broken into a much simpler integral by using this technique. We had a product that we did not know how to integrate, but now it's going to give us something simpler that we know how to integrate. U times v is x times sine of x, x sine x, minus v du, which is sine x, and du is just equal to dx. Well, we do know what is the integral of sine x. Integral of sine x is negative cosine x. That would actually become a positive x plus c. So as you can see, this technique is helpful in breaking an integral that's harder to break into an integral that is a lot easier to evaluate. All right, let's look at the next example. We have x times natural log of x dx. Again, no other technique of integration that we've talked so far is going to work here. U sub is not going to work. No other techniques are going to work. So let's go ahead and start thinking about what are we going to call u, what are we going to call dv. U is going to be, think about Liet. So whatever comes first in the list, we're going to call that u. Looks like there is a logarithmic function, and that's what's going to be my u. Go ahead and do the derivative. Du would be 1 over x dx. Okay, go ahead and integrate dv. Sorry, dv would be x dx. Go ahead and integrate both sides. So when you integrate both sides, v comes out to be x squared over 2. I'm not worried about the constant of integration yet because eventually there's gonna be another constant, and I will put a constant at the very end of my answer. So let's go ahead and write down our integration by parts formula. U dv is equal to uv minus v du, and that turns out to be x natural log of x is equal to u times v. U is natural log of x, v is x squared over 2. So x squared over 2 times natural log of x minus v du. Du is 1 over x dx. Okay, go ahead and simplify. So we have x squared over 2 natural log of x minus, one of the x's can cancel. I can pull out the 2 in the front. What's the integral of x dx? It would be x squared divided by 2 plus c. Turns out to be x natural log of x dx is equal to x squared over 2 natural log of x minus x squared over 4 plus c. Okay. All right, another example. Let's look at example number 3, x cosine 3x dx. Again, u sub is not going to work here, so we got to think about integration by parts because we have a product over here. First thing I need to decide what's my u, what's my dv. Looks like using Liat, u will be x, Liat, however you want to call that. dv would be cosine 3x dx. This is the one that we're going to differentiate, and this is the one we are going to integrate. Okay, differentiate du turns out to be equal to dx. When I integrate, I get v is equal to 1/3 sine 3x. It's a 3 here. 1/3. Okay. 1/3 sine 3x. All right. Now let's go ahead and write u dv is equal to uv minus v du. So x cosine of 3x dx is equal to u times v, which would be x over 3 sine 3x minus v du. Du is just dx. Okay, I can pull out a 1/3 from the integrand, so it turns out to be x over 3 sine 3x minus 1/3. What's the integral of sine 3x? It is 1/3 cosine 3x, but negative. So that makes it a positive here. So I'm left with x/3 sine 3x plus 1/9 cosine 3x plus c. Okay. That's it for this problem. Let's check out our next problem, number 4. X plus 4 e to the power negative 5x dx. Again, I got a product here and use substitution is not going to work. So we're going to think about integration by parts. Let's think about what's going to be my u, what's going to be my dv. U is going to be, think about Lie, logarithmic, inverse trig, algebraic. There is an algebraic function, x plus 4, and then exponential function would become my dv. Okay, and remember we are going to differentiate here and we are going to integrate here. Okay, when I differentiate du dx, well, I can write it like that, or I just prefer writing du is equal to dx. Or you can say du over dx equals 1, and then if it makes more sense, you can write it du over dx equals 1, and then du is equal to dx. Integrate, so we would be left with v on the left hand side. V equals e to the power negative 5x divided by negative 5. So that's my v. Okay, now let's go ahead and write down the formula for integration by parts. U dv is equal to uv minus v du. Plug everything in there. X plus 4 e to the power negative 5x dx equals u times v. Okay, u times v. Here's u, here's v. U times v, which is x plus 4 times negative can come in the front, 5 can go here. U times v minus v du. E to the power negative 5x over negative 5. Du is just equal to dx. Okay, so negative x plus 4 over 5 e to the power negative 5x plus integral. I can pull out the 1/5 in the front, e to the power negative 5x dx. Okay, the integral of negative e to the power negative 5x, I can divide it with negative 1/5. I will have to when I do the integral. So it will become negative 1 over 25 e to the power negative 5x plus a c. And that's our integral. Okay. Next problem, let's check that out. If I let natural log of cos x as u here, then I would have 1 over cos x times sine x as du. So u sub is not going to help me out here. If I just let cos x as u, then I have sine x dx as du, so natural log of u. And what's the integral of natural log of u? We haven't worked on that yet either. So let's go ahead and use integration by parts because we have product of two functions of x. I need to first start by dividing or deciding what is my u and what's my dv. Again, Liad might help. U is going to be natural log of cos x and dv would be sine x dx. I'm going to differentiate the first function and integrate the second function. Okay, differentiate this one. So du turns out to be 1 over cos x times negative sine x dx. Or I can say negative du is sine x over cos x. Sine x over cos x is tangent dx. Or I can say du is negative, let's just leave the negative here for a minute, not to, it's okay to leave it there for now, tangent x dx. Okay, so I know what my du is. Now when I integrate v, that turns out to be negative cosine x when I integrate dv, both sides. Okay, my integration by parts formula is, it's often written as IBP, integration by parts, is u dv is equal to uv minus v du. Okay, u times dv, which is sine x times natural log of cosine x dx, equals u times v. U is natural log of cos x times negative cos x minus, that's too long of integration symbol, minus v du. V is negative cos x times du is negative tangent x dx. Okay, let's just clean it up a little. So we have negative cosine x times natural log of cosine x. And I see 3 negatives here, so eventually I would have something negative cos x. I'm going to write tangent x as sine x over cos x dx. Okay, we can cancel the cos x and cos x, and we are left with negative cos x natural log of cos x minus, what is the integral of sine x? Integral of sine x is negative cos x, so it would actually become a positive because there's already a negative sitting over there. So this is what our integral turns out to be after simplification evaluation. Okay. Next example, we're going to look at number 6 now. Integral of natural log of x dx. So far we have not found out. So far we have not found how to find, so far we don't have any formula to find integral of natural log of x. We know so what is the integral of 1 over x? Integral of 1 over x is natural log of x. What is derivative of natural log of x? Derivative of natural log of x is 1 over x. But we have not discussed integral of natural log of x. So we got to use a clever technique here. We are going to multiply by 1. Multiply by 1. There's no reason, and when you multiply with 1, you're not really changing anything. So I'm going to write this integrand as natural log of x times 1 dx. Now if I think about Liat technique, I see natural log of x will be my u and dv would be 1 dx. Okay, by multiplying with 1, we are able to write it as a product, and we can use integration by parts. And again, differentiate and integrate here. When I differentiate u, it turns out to be du is 1 over x dx. Du turns out to be 1 over x dx, and v turns out to be just an x. Okay, let us see now what else. What does it turn out to be? Okay. Go ahead and write our integration by parts formula. U dv is equal to uv minus v du, which turns out to be u times v. V is x, u is natural log of x minus v du 1 over x dx. As you can see, this has simplified our life so much because the x and x will actually cancel, and we'd be just left with 1 dx. And that turns out to be x natural log of x minus x plus c. So now remember, this is something you should add to your list of integration rules that so far we had not evaluated natural log of x. It's always equal to x natural log of x minus x plus c. This will come back in use in future next few chapters, so make sure you remember this formula as well. Natural log of x dx integral is equal to x natural log of x minus x plus c. All right, next example. Inverse trig function integral. Well, we know derivative of sine inverse x, and we know that if I do the derivative of sine inverse x, it is 1 minus x squared. We have proved it using implicit differentiation in Math 1a. We also know if I do integral of 1 minus x squared dx, then that turns out to be sine inverse x plus c, but we don't know what's integral of sine inverse x dx. Okay, so what we're going to do is, again, the same technique. We're going to multiply by 1. Using Liat, u would be sine inverse x, dv would be 1 dx. Okay, du turns out to be, I am going to differentiate the u, 1 minus x squared dx, and v turns out to be just an x. Integration by parts formula is, integration by parts is u dv equals uv minus v du. Okay, let's plug all the values in. U times v, u, okay, that would be x sine inverse x equal to, so on the left hand side I have just sine inverse x, or times 1 if you want. Clean it up a little. Times 1 dx. This is going to equal uv, rewrite it. All right. Sine inverse x times 1 dx would be u times v, which is x sine inverse x minus v times du, 1 over square root of 1 minus x squared dx. Now, this piece looks like a good candidate for u substitution, so I'm going to evaluate that on a side here. Integral of x over 1 minus x squared dx. If I let 1 minus x squared as u, negative 2x dx is du, x dx is negative 1/2 du. Okay, so my top is negative 1/2 can be pulled out, du over square root of u, which turns out to be, we can take it to the top. This can be written as negative 1/2 u to the power negative 1/2 du. When I add 1, so it's negative 1/2 times negative 1/2 plus 1 is positive 1/2. Divide with positive 1/2 means multiply with 1/2. So it turns out to be negative u to the power 1/2 here, and the u was 1 minus x squared. Okay, so just a simple u substitution. This integral would turn out to be x sine inverse x minus, and there's going to be two negatives. That would make it a positive. There's already a negative here and a negative in front of the u to the power 1/2. And u was 1 minus x squared raised to the power 1/2 plus c. And that's what this integral comes out to be. If you're ever in doubt, you can go ahead and do the derivative, differentiate this function, and you should get this back. Okay, next problem. Let's see, this was number 7, so there's number 8 as well. Tangent inverse x. Pause for a minute, stop, and you go ahead and try it, and then come back and check with me. Tangent inverse x times 1 dx. Again, the same technique I'm going to use. Let u be the tangent inverse x, dv be 1 dx. du will be 1 over 1 plus x squared dx. v would be equal to x. Now when I do u dv, uv minus v du, integration by parts, let's see what does it turn out to be. Tangent inverse x times 1 dx is equal to u times v which is x, tangent inverse x minus v du, which is x over 1 plus x squared dx. Again, this is a good candidate for u substitution, so I'm going to do that on a side and plug it back in there. Integral of x over 1 plus x squared dx. Let 1 plus x squared be u, 2x dx be du. X dx would be 1/2 of du. Okay, so it's 1/2 du over u, which is 1/2 natural log of u, which is 1/2 natural log of 1 plus x squared. All right, we're ready to plug this back into where we left with. So the integral tangent inverse x dx, it doesn't matter if I write 1 or I don't. It turns out to be, so that piece comes down, and we just evaluated this little piece in the on the side over here. So that turns out to be minus 1/2 natural log of 1 plus x squared dx. No, dx, plus a c. And that's the integral of tangent inverse x. Okay. All right, good. Next problem. We have seen several examples of integration by parts now. This one, as you can see, I said going in circles. There's a reason why I said that. Let's go ahead and check that out. So what are we going to call u here? What are we going to call dv? Let's see if Liat helped me out. Okay, Liat says logarithmic, inverse trig, algebraic, trig functions, and exponentials. So it looks like trig functions come first in the list. So sine x will be my u. dv would be e to the power x dx. Okay, go ahead and differentiate and integrate dv and see what does it turn out to be. So du would be cos x dx, and v would be just e to the power x. So let's go ahead and simplify our formula. U dv is equal to uv minus v du. U is sine x, e to the power x. Well, let's just write the way it was in the beginning. It doesn't matter when you're multiplying. So we have e to the power x sine x dx. It's very important that you start the problem correctly. Use correct choice for u and dv. If your choice for u and dv are not correct, you will be not able to evaluate that integral. So e to the power x sine x dx is equal to u times v. U is sine x, v is e to the power x sine x, minus v du. V is e to the power x dx. Du is cos x dx. So I'm going to call this number 1. And as you can see, this is not much easier than what we started with. We started with product of e to the power x and sine x. And now we're stuck with product of e to the power x and cos x. Okay. Now what I'm going to do is I'm only going to focus on this little piece on a side. And I will come back and plug my answer into where I left off. Okay. So e to the power x cos x dx. Again, I'm going to do integration by parts one more time. We did integration by parts in the beginning, and now we have to do integration by parts one more time. So what's going to be my u here? What's going to be my dv? Okay, the u will be cos x, again using Liat. dv would be e to the power x dx. All right. This gives me du is equal to negative sine x dx, and v is e to the power x. Okay, now e to the power x cos x dx, u dv is equal to u times v, which is e to the power x times cos x, minus v du. V is e to the power x negative sine x, so I'm going to bring the negative out and make that positive. Okay, let's call this number 2. Now, if I plug this integral's value in here. Let us see what happens. Reason why we called it going in circles, we got our original integral back over here one more time. So we can keep on doing it as many times as we want. We would keep on getting our original integral back. So at this point, I'm going to stop and plug it back into, plug the number 2 into number 1. So we started with e to the power x sine x dx is equal to e to the power x sine x minus this entire integral is equal to e to the power x cos x minus integral of e to the power x sine x. Because I'm plugging it back in, the negative will get distributed and it would turn both of these factors into negative sign. It will multiply with -1 because of the negative sitting in the front here. Okay, power sine x dx. Now what I'm going to do is I'm going to take it to the left hand side. So I have e to the power x sine x dx plus e to the power x sine x dx equal to e to the power sine x minus e to the power cos x. There is a plus c here as well. I'll take care of the plus c at the very end. So this is twice of e to the power sine x dx. That turns out to be e to the power x sine x minus e to the power cos x. Now we can divide both sides with 2. So this integral we evaluated and it turns out to be e to the power sine x minus e to the power cos x divided by 2 plus c. Okay, so we evaluate that integral and it turns out to be e to the power x sine x minus e to the power cos x divided by 2 plus c. All right, next example, number 10. X squared sine of x. Let's see, x squared sine of x. First thing, again, u sub is not going to work in any of these problems, so I'm not trying u sub. I'm going to use integration by parts because I see a product. Integration by parts does not always work either. So there are going to be some cases where integration by parts does not work. So u and dv. Think about liat. What's going to be your u? What's going to be your ve? dv, algebraic functions comes first. So x squared is u, dv is sine x dx. Do the derivative, du is 2x dx. And we would be integrate the sine x, that would be negative cosine x. Okay, now u dv equal to uv minus v du. So plug all the values in there. This is going to leave me with x squared sine x dx equal to u times v, which is u is x squared, so negative x squared cosine x minus v du, negative cos x times 2x dx. Okay, negative cos x times 2x dx. All right, this comes out to be negative x squared cosine x. I can pull the 2 outside, I can pull the negative sign outside, and I'm left with cos x times x dx. And I need to do integration by parts one more time over here. Integration by parts again. So that's cos x times x one more time I have to do. Let's see, I think this was the very first problem we did. So we can just get the answer for this part from there, or you can go ahead and do integration by parts. I'm going to just point you to it. This was the very first problem we did. X cos dx integration is x sine x plus cos x plus c. So I'm going to steal the answer from here, but if you had not already done this, then you have to do it one more time. Okay, so negative x squared cosine x plus, let's see, there's a 2, so plus 2x sine x and plus 2 cos x. So I just got the answer from the previous problem number 1. We did this. This was example number 1 in this video. Okay, so I'm just getting the answer from there. And this is the integral that we would be left with. All right, some more examples. Some of them will have bounds in there. Even if you have the bounds, story doesn't change. It's still the same process. Just remember to plug the bounds in correctly. So let's go ahead. Okay, here's number 11. X squared e to the power x dx from 0 to 1. All right, so I'm going to do integration by parts. Again, u sub is not going to work. So I'm going to say let u be, think about what u should be here. U should be x squared, dv would be e to the power x dx. V is going to come out to be e to the power x, du will be 2x dx. Okay, u dv is equal to uv minus v du. Notice we're not changing our integral into the u form, so no need to change the bounds. Okay, so x squared e to the power x dx going from 0 to 1 is equal to u times v. U is x squared times e to the power x from 0 to 1 minus the integral going from 0 to 1 v du e to the power x times 2 times x dx. We can pull, let's just call this number 1. I'm going to spend some time on evaluating the integral now, and it looks like I have to do integration by parts one more time. So I'm just going to take care of the second integral really quick. So I'm going to focus only on this piece for now, and then I'll plug it back into 1 and plug the bounds in. Okay. So let's check. All right. 2 e to the power x times x dx going from 0 to 1. All right, so again, another u sub here. Use a different color. So let u be x and dv be e to the power x. Du will be dx, v will be e to the power x dx. dv is e to the power x dx. Okay, so we are doing x u dv is equal to u times v, which is e to the power x times x from 0 to 1 minus v du. V is e to the power x, du is dx. That made it so much nicer because I know how to evaluate the e to the power x from 0 to 1 integral. Okay, so let's see what does that turn out to be. It turns out to be e to the power x times x from 0 to 1 minus e to the power x from 0 to 1. Let's see what does this integral turn out to be. I'm going to plug the 1 in there. E to the first power times 1 minus e to the 0 power times 0. That would be just 0. Minus e to the first power minus e to the 0 power. Okay, so I have e minus e to the first power times 1, which is e, minus 0 times something is 0, minus e to the power 1 minus e to the power 0. Okay, so minus e plus 1. It looks like it just turns out to be this piece. These two cancel and we just have 1 left over there. Now go back, plug into 1. So again in 1, we were doing 0 to 1, x squared e to the power dx. That turns out to be, plug a 1 in there, plug the bounds for this piece. So we have 1 squared times e to the first power, which is just e to the first power, minus 0 times something is just 0. And then minus 1. So it turns out to be e minus 1 is my final answer. E minus 1 is the integral I'm left with after simplification. Evaluating this integral, it turns out to be e minus 1 is going to be the area under the curve from 0 to 1 for this curve. Okay, next example. Let's see, how many do we have more? We have a couple more. 1 to 2 x cubed natural log of x dx. You should try it by yourself because we have done a few problems by integration by parts now, and then come back and check. So let's see. So in this case, I'm going to call u as natural log of x, dv as x cubed dx. Du is 1 over x dx. V is x to the 4th over 4. So that turns out to be 1 to 2 x cubed natural log of x dx. Again, we're not changing our integral into u integrals, so no need to change the bounds. Okay, u times v from 1 to 2 minus the integral of 1 to 2 v du, x to the 4th over 4 times 1 over x dx. Notice it broke our product into a much nicer integral that we can easily evaluate. So I'm going to plug the bound 2 first in the first parentheses, in the first portion. 2 to the 4th power over 4 natural log of 2 minus 1 to the 4th power over 4 natural log of 1. And natural log of 1 is 0, so this piece is all going to be 0. Minus the integral, we can pull out the 1/4 outside, and x to the 3rd dx. Again, the bounds are from 1 to 2. So it turns out to be 2 to the 4th power is 32. 32 divided by 4 is 8 natural log of 2. 8 natural log of 2 minus 1/4 x to the 4 over 4 from 1 to 2. 8 natural log of 2 minus 1/4 2 to the 4th power over 4 minus 1 to the 4th power over 4, which turns out to be 8 natural log of 2. 32 divided by 4 is 8, right? Oh, 1 second. There was over 4 as well here. Okay, 2 to the 4th power. Two to the 4th power is 16, my bad. Apologies. So this is not absolutely correct. 2 to the 4th power is 16. 16 divided by 4 is 4, my bad. This 2 to the 4th power, 2 to the 5th power is 32. I apologize. That is not correct. Okay, so 4 natural log of 2 minus 1/4, and again 16 minus 1, this is 15 over 4, which is 4 natural log of 2 minus 15 over 16, and that's the definite integral that we just simplified. I believe there's 2 more examples. 0 to 1 natural log of x plus 1 dx. Again, there's no other way to evaluate this integral. So what we're going to do is natural log of x plus 1, bring a 1 by yourself. Okay, now I'm going to let u be natural log of x plus 1 and dv be 1 dx. If I integrate dv, I can say v is equal to x. And if I differentiate u, I can say it's 1 over x plus 1 dx. Now break our integral. U dv is equal to uv minus v du integral. Don't forget the bounds. So I'm going to do that now. Use a different color. 0 to 1, natural log of x plus 1 times 1 dx is equal to u times v, which is x times natural log of x plus 1 from the bound 0 to 1 minus v du, which is x over x plus 1 dx. How do you evaluate x over x plus 1 dx? Let's see, x over x plus 1. Okay, I guess we have to use a clever technique here. So what I'm going to do is I'm actually going to call this number 1, this whole equation or this whole expression number 1, and I'm only going to focus on this piece for a minute. Okay, let's see. What does x over x plus 1 dx, how do I evaluate this? So use a clever technique or clever trick of add and subtract 1. Add and subtract 1. So this would turn out to be x plus 1 minus 1 over x plus 1 dx, which we can write as separate fractions, and we can break the integrals. 1 over x plus 1 dx. So this is just going to leave me with 1 dx minus 1 over x plus 1 dx. Okay, 1 dx is just x, and this integral does have derivative of the bottom is sitting on the top, so it's just, you could use a u substitution, or you could just see directly that it's going to be natural log of x plus 1. Again, I'm not bothered about c yet. I'm going to put in a c at the very end of my answer. So x minus natural log of x plus 1 is what this integral comes out to be once we evaluate. And again, don't forget the bounds are still from 0 to 1. So we are going to plug 2 into 1. Plug 2 into 1. So our integral that we started with natural log of x plus 1 from 0 to 1, natural log of x plus 1 dx, it turns out to be equal to, I'm going to start plugging the x, natural log of x plus 1, the bounds are from 0 to 1, minus x minus natural log of x plus 1, bounds are 0 to 1. There's no need to add a c, it was a definite integral, so no need to add the c in here. It's a definite integral, okay? Let's go ahead and plug the bounds in and see what do we come up with. If I plug a 1 in there, 1 times natural log of 1 plus 1 is 2, minus 0 times something is just 0, so no need to write it. And inside the parentheses, I would have 1 minus natural log of 2 minus 0 plus natural log of 1. Natural log of 1 is also 0, so no need to write these. So I'm left with natural log of 2 minus 1 plus natural log of 2, which is 2 natural log of 2 minus 1. 2 natural log of 2 minus 1 is what I'm ending up with, okay? It looks like that would be our final answer here. All right, next problem. I think it's the last problem for this section. Let's go ahead and take a look at this. Could I, can I use integration by parts here? So now the thing is, both are algebraic functions. X cubed is algebraic and square root of 4 minus x squared is algebraic. So we don't know. Liad does not help us decide what's going to be your u and what's going to be your dv. Remember, you want the more complicated part that is easier to integrate. You want that to be dv. Complicated part that is easier to integrate, you want it to be dv. And the part that is easier to differentiate, you want that to be u. So what I'm going to do here is I'm going to call x square root of 4 minus x squared dx as dv. And then x squared would become my u. Du would be 2x dx, or I can say x dx would be half of du. and integrate v. So when I integrate both sides, this can be done using the u substitution. So I can go ahead and use a u substitution here, u sub, because the derivative of 4 minus x squared is sitting in the front. I'm not going to call it u, I'm going to call it t or something. Let t be 4 minus x squared. dt is negative 2x dx. Or I can say negative 1/2 dt be x dx. So it does turn out to be negative 1/2 square root of square root of t. We're calling it t dt. And when I do the integral, this is going to be t to the power 1/2 plus 1 would be t to the power 3 over 2. Divide by 3 over 2 means multiply by 2/3. This comes out to be negative 1/3 t to the power 3 over 2, which is negative 1/3. T was 4 minus x squared to the power 3 over 2. So that's what this integral turns out to be. Okay. All right. So let's go ahead and use our integration by parts technique. This problem can also be done using direct u substitution. I'll also show you that as well. But this can be also done using integration by parts. I think it might be easier to do u substitution here than it is to do integration by parts. Okay, so integration by parts is u dv is equal to uv minus v du. So u dv, which is x cubed square root of 4 minus x squared dx, is u times v. U times v. U is x squared, and v is times negative 1/3. This is equal to v, because we integrated. That's what we had done. Let's not call it u substitution, let's just call it t substitution, but because we didn't use the u letter here. Negative 1/3 4 minus x squared to the power 3/2 minus v times du. Negative 1/3 4 minus x squared times 3/2 times du. Du is 2x dx from here. Okay, I did not need this. All right, so simplify a little. Turns out to be negative x squared over 3, 4 minus x squared 3/2, plus 2/3 can be pulled out, x times 4 minus x squared 3/2 dx. Okay, another u substitution here. So another u substitution problem. Another u substitution problem here. I'm not going to call it u here. I'm going to call it y now. So I'm only going to focus on this integral. And once I have evaluated it, I will plug it in. Okay, the highlighted integral that I have. That's the one I'm going to focus on now. So x times 4 minus x squared 3 over 2 dx. Let's just call this number 1. All right, so let's use the y substitution. Let y is equal to 4 minus x squared. dy is equal to negative 2x dx. Or we can say negative 1/2 dy is equal to x dx. X dx. Okay, so ready to plug the values in. This integral will turn into y integral. So it turns out to be negative 1/2, comes out in the front, and sorry, not the u, we're calling it y to the power 3/2 times dy. Okay, which is negative 1/2. Y to the power 3/2 plus 1 is 5/2. Divide with 5/2 means multiply with 2/5. So 2 and 2 is cancelled, which is negative 1/5 y to the power 5/2. And y, what did we call the y? 4 minus x squared. 4 minus x squared to the power 5 halves. Okay, now plug this number 2 into number 1. Plug 2 in 1. Let me use a different color now so that it's all easily visible. All right, so our integral that we started with, it was x cubed square root of 4 minus x squared. Turns out to be negative x squared over 3, 4 minus x squared to the power 3 over 2 plus 2/3 times negative 1/5, 4 minus x squared times 5 to the power 5 over 2 plus c. One last simplification, negative x squared over negative x squared over 3, 4 minus x squared, 3 halves, minus 2/15, 4 minus x squared to the 5 halves plus c. As you can see, it was a long problem. I believe you can also do this using trig substitution. When we get to the trig substitution, we will look at this problem using trig substitution as well. But really quick, let's give it a try and see if it's doable using u substitution. Okay, the integral is x cubed square root of 4 minus x squared dx. If I would do the maybe I'll use blue color, use substitution. So if I wanted to use direct, so another method, I think it will work out. Another method for this problem, direct use substitution. Let's see. So if I let 4 minus x squared be u, then negative 2x dx be du, and I can say x dx be negative 1/2 du. And I can break the x cubed into x squared and an x dx, because x squared times x will be x to the 3rd power. Now I have a way to write x dx in terms of du. It's 1/2 du. And from here, I can say x squared is 4 minus u. X squared can be written as 4 minus u. So this integral will turn into 4 minus u, square root of u, and then negative 1/2 du. Okay, we can distribute the u's inside. This is a u, the first one is a 4. Okay, we can distribute the square root of u inside and then go from there, evaluate the separate the integrals and evaluate from there. So it turned out to be 4 square root of u with negative 1/2 in the front, minus u square root of u du. Add the exponents, evaluate the integrals, and that should be also doable. Okay, that was the end of the integration by parts examples.